So actually, any concrete section exposed to axial load and moment, you can treat it this way. With this slide set, you're going to see equations, you're going to see maybe a software, things like that. Since we have mainly axial load, I'm going to quote a column, but in many cases, you have a beam exposed to axial load and moment. You just handle it the same way. Axial load here is going to be equal to P sub U, and the moment is going to be equal to P sub U times E, the eccentricity. Here's the moment. When the eccentricity is going to be getting larger, the amount of moment is going to be much larger than that when P sub U is going to be at smaller eccentricity. If you put P sub U right at the dead center, which means at the centroid of this column, is going to be only pure compression. It's going to be like this equation. If you put here E to be equals to 10% of H, someone's going to say, what is H? I'm going to say H is going to be this depth from this point to that point. I'm going to call this to be H, total depth. So I'm going to say here, I'm going to put here this text box. I'm going to say when E equals 0.1 H, what's going to happen? We're going to have a small eccentricity. And in this case, the axial capacity is going to be the same as this equation. But phi Mn that's going to go with it is going to be equal to this phi Pn multiplied by 10% times H. Why? Because this is going to be like this box here. It says P sub U times E, and your E in this case is going to be 10% of H. Okay? Looking here in the interaction diagram, this is going to be here the moment versus the load P, axial load. And the interaction diagram here that you're looking at does not include the phi factor. So you can call this here to be Mn versus Pn. When you apply the phi factor, interaction diagram is going to be shrinking a little bit. When the phi factor here at axial compression is going to be 0.65, you're going to see lots of shrink. But here, towards the pure moment, is going to be only 0.9. This here, the relationship between the 0.65 to the 0.9. In the top here, you have axial compression, because moment is going to be equal to 0. And at point F, you're going to have here pure moment, and axial force is going to be equal to 0. So now I understand 2 points. Point A, I have an idea about it. I have done it. Point F, I have done it before. Point G is going to be pure tension. And in pure tension, the strength, as we have discussed it, and we did one example on it, is going to be equal to the phi factor, the 0.9, times AS times Fy. We have here some point, which is right here. Look at this. Very important point. I'm going to call it here the balanced point. At the balanced point, I'm going to have this balanced condition in the strain. The strain in the concrete is going to be equal to 0.03. So I'm going to say this is going to be here 0.003. And the strain in the tension steel is going to be equal to the yield point. For grade 60, I'm going to say here, right? For grade 60, steel, the strain equals to 0.0021. The points of interest that I care about when it comes to, let's say, a midterm or maybe a final is going to be this boxed points. Axial compression, yeah. Balanced point, yeah. And it's going to be a simple one to do the analysis for. Because when the strain here is going to be 0.0021 and the strain here is going to be 0.03, it means finding out the neutral axis depth is going to be easy step. Not going to be that tough. This point here is like beams. We have done beams. This point here is going to be much easier than beams. It's going to be just AS times Fy times the phi factor of 0.9. Any questions on that? Any questions? Okay, good. Look at the amount of reduction here. Shrink from this side. You see here's going to be the 0.65 and this is going to be the 0.9. This is why in this side, the reduction in the capacity is going to be much more than that from that side. And for the small eccentricity, I'm going to chop off this piece. And this explains this factor that here you're looking at, the 0.8. You see, look at this. This factor here, the 0.8, the constant. What is this constant for? I'm going to say this is going to be for the small eccentricity effect. So you cut here 20% of the total capacity, meaning this term here, you see here this term that I just put on a box. If I come here and then write it to be P sub 0, right? This is going to be P sub 0 and this is going to be phi Pn. Let me go here. This point here is going to be this one that I'm just looking here at. Look at this. This point is going to be P sub 0. So I can maybe put a text here. I'm going to say this is going to be P sub 0. So this equation is going to be this guy here. Once multiplied by phi factor, the 0.65, you're going to be coming right here at this point. So this one here is phi factor, the 0.65 times P sub 0. I say, how about this one? What is that point for? You see, this point is the phi times the phi, which is a 0.65, times the 0.8, the reduction, times P sub 0, which we called here phi Pn in this equation. And the 20% reduction is going to be from here to there. Look at this. Why? Because from here to there, you apply this 0.8. If this can be like 100 kips, this is going to be 80 kips to there. Okay. This is here an output from a software, PCA column. If I give you here the Excel load on the column, you can figure out Pman. Or if I give you here M sub U, you can figure out the capacity of the column under this given moment condition. We have an example. We said that the important sections is going to be the small eccentricity and the balanced strain condition and the pure tension. I know that I went through this, but I'd like just to review it quick so that if you guys have any questions, please come with it. Just say it. Small eccentricity, balanced section, C, and then pure tensile capacity, tensile strength. For the first one here, the pure compression, small eccentricity, I have the cross-section area of the column. I have AST, amount of steel, vertical steel. I can apply my equation here. It says here 672 for this axial compression point. You're gonna say, where is this point? I'd like to see it on the diagram, on the interaction diagram. I'm gonna go back here and say, this is gonna be this point here. So let me put it right there. Let's give you the first point. Let me put a different color. Let's put it here in green. Let's give you the first point. Let me keep this. This is gonna be slide number 6. So 672 is good. And then it says here, for a small eccentricity, the E is gonna be equal to 10% of H. Total depth is 20 inches according to this given information. Here's H, 20 inches. Take 10% of it. It's gonna be 2 inches. Right? 10% of the 20 is gonna be 2 inches. Divide by 12 is gonna be E. So this term here is gonna be E in feet. Multiply by 672 is gonna give you this moment capacity. Now I need to go back there on slide number 6 and show this. So I'm gonna say, which moment are you talking about? I'm gonna say axial load level is the same. So I'm actually talking about this point. give you the amount of moment that you're talking about. Just give it from here to there. Also a vertical line that goes to this moment value. Okay, I'm gonna say, okay, this much moment accounts for 10% times E. 10% of E, and then multiply by the axial load. So now I have this point and that point. For me, it's like the same point because this gives you the same axial capacity, right? But this axial capacity, what the code says, it's not going to change as long as your moment is going to be within this small eccentricity moment, which is 10% E, which is 10% times H multiplied by the axial load capacity in here. So, okay. Now I need to jump to the balance condition. When the strain in the concrete is going to be 0.03, the strain in the steel is going to be 0.02. Why 0.02? This is because this is about E sub y, which means strain at yield. Just happen here to be 0.002. For that, I should be able to figure out C sub B. It turned to be 10.2 inches. Just one equation, one unknown. So this is going to be a simple analysis. Figure out the C. Once you have the C, you can also figure out A, which is 0.85 of this. Take 10.2 times 0.85, it gets you compression block depth. Why do you need compression block depth? Because it's going to help you with the C1 value, the compression force in the concrete. The other question is, out of this equation here, once you have the C, can you figure out the strain in the compression steel? Say, why is that? Because I need it for the second compression force, which is the compression force in the compression steel. Finding out the strain in the compression steel. How do you do this? You say 0.03 divided by C equals to epsilon S prime divided by, I'm going to say here, C minus D prime. What is D prime? D prime is going to be this distance, which is 3 inches. 3 inches top, 3 inches bottom. With that, I was able to find out the strain in the compression steel, epsilon prime S. And with that, it's going to be equal to the yield. Therefore, the stress in the compression steel is going to be equal to 6 KSI. Let's give it right at the yield point. First compression force, which is given in the concrete. Now I have the A depth, 2.85 C sub B, right? This is giving the A value, which is right here. Here's the A value. The width of the web is going to be 14 inch times 0.85 prime C, right? Actually, the whole thing here is going to be your A, 0.85 times CB. Now I have the first force, compression force. Now second compression force that I need is going to be compression the steel, right? Here's the compression the steel only, but I need to subtract this component because I don't want to double count this cross-sectional area of the steel twice. When you go back here, here's the depth, right? I can just look at this way and say, okay, here's the concrete area, exposed to compression, right? Which is a red box, but also I have the steel kind of double counted, so I need to get rid of it. We're going to subtract here 0.85 prime C times AS prime. I have here 170 caps. At any time that you do this C1 and C2, like what happened in the first midterm, when it comes to the problem that you have a T section or compression steel, some people would say, here's the T section, I'm going to have C1 and C2, but they don't look at the tension force. They need to say tension equals compression. In this case, the C2 is already pre-solved. And the C1, the depth of it, is going to be based on the amount of tension that you see here. Now, when you do summation of the force equal to 0, you cannot ignore this external applied force. So we're going to say this force is going to be equal to the difference between compression force and the tension force, turned to be 403 caps. You'd like to figure out the amount of eccentricity, this E. So what you need to do is just take the moment about this point. all the forces. Come here, I'm going to say C1 times Z1 plus C2 times Z2 equals P sub B times E plus the 7 inches from here to there. Let's give you 7 inches. So I can write it down. Why 7 inches? Give you 1/2 of this 14 inch. Put that as all for E. So now I can apply the phi factor. If you take this number here, multiply by the phi factor of the 0.65, you get phi PN. If you take this number here, multiply by the eccentricity, here's eccentricity, you got phi man. Phi man is going to be the same as this. So let me write this down. I'm going to say this is going to be the same as, you can call it here phi man. Any questions on the balance of point? You're good? All right. Pure tensile strength or capacity, you just take AS, here's AS, times F sub Y, yield strength, times the phi factor 0.9. Now I'm done with this. All right, now let's switch gear and move to foundation design. Unless you guys have any questions. Questions? You're good. All right. Foundation design here. It is one set of slides, and this is a good size one. You have here 63 slides. Usually foundations give you this interface between the building and between the soil. The job of this footing or this foundation is to take the load from the columns or the walls and transfer it to the soil. Concrete is very strong compared to the soil. So the issue here that this footing is going to be penetrating the soil under this vertical load. So when you do this, when you size the footing, you need to be sure that the contact pressure between the soil and the footing is going to be within the allowed value of the soil, not the concrete. Because as his concrete is going to be strong. So the bearing pressure on the concrete coming from the soil is going to be easy to be handled by the concrete. The whole problem here is going to be in the soil. The contact pressure here and the size of the footing is an ASD design. Did you guys hear this before? ASD, we talked about it. Allowable strength design. Strength, sometimes you call it stress design. What is allowable strength or stress design? This is when you take the service loads. Someone's gonna say, what is service load? You're gonna say service load, you're gonna say such as dead load, life load. Just the pure value of dead load and life load without having load factors or ultimate load, this is what we call here service load. When you just add dead load to life load, I call this here service load. Let's say this come here, service load. So when you size the footing, when you check the allowable bearing pressure of the soil, this is going to be called here ASD design. Same thing, here's the footing. So this footing sometimes supports gravity load, like dead load and life load. Sometimes also supports seismic loads, like lateral loads, earthquake forces, and wind forces. They're supposed to transfer it to the soil. Here's one pavement, and then you see here some column footings. You can call it a pad or a column footing. And the pavement walls here, you're going to have continuous footing for the wall, right? Their job is to take the loads from the top levels and transfer it to the soil. Like what happened here? This is going to be the load path that we looked at this slide before once. You can have point loads, uniform load, like service load or line load, transfer from the slab to the beams, to columns, to footings, eventually to the soil. Another picture here, 3D, here's a pad for the column, and you have here continuous footing is going to be for the wall. Now, think about this footing, and of course, you're going to have reinforcing inside it. Column reinforcing is going to be this vertical, and the tie is going to be like this. So this column reinforcing is to make the column itself strong and to be able to resist the given loads. And we learned about the tie design, about the vertical reinforcing bar design, about the capacity of the column itself. Any questions? Yes? No questions? Are you guys there?
Yeah, I'm here.
Yes.
All right. Right.
Yes.
Questions? Right. Good. No question. Now, in the footing itself, I'm going to put the reinforcing. And if you look at this, you have a mesh, like you have it in both directions. And you see here, the reinforcing is mainly at the bottom. I'm wondering, do I need reinforcing here to be in the top or the bottom of the footing? Let's give it the total thickness of the footing from here to there. But the reinforcing itself plays at the bottom. We look at this section here. Here's a plan. It shows a mesh in both directions. And look at this. Main reinforcing is going to be at the bottom of the footing. So I'd like to see here, what is the effect when you add here axial load on this footing? What type of deformation should I expect? And if I may exaggerate, you can be looking here at this section. Look what happened. Here's the footing. You put axial load. What happened? The soil pressure is pushing upward. And it wants to bend this way, meaning tension is going to be at the bottom. So I'm going to write here tension is going to be at the bottom. Compression is going to be at the top. So, okay, here's tension compression. Now, where do you want to put the steel? Yes, here reinforcing bars, of course, is giving the tension side. Why do I need a mesh? Why do I need both directions, this reinforcing bars? Let me check this out. And say, because when you put here an axial load, this side here, this line, if I may call this line AB, look at this. Here's A, here's B, and here's C. Line AB wants to lift up in this direction, right? At the same time, also line this BC wants to lift up in this direction. Meaning I'm gonna have here bottom tension in this side, very close to the column, and bottom tension in this side, parallel to BC. Now, where is the maximum moment? Let's say maximum moment, let me look at this. This looks like a cantilever system with some uniform load, like in here, look at this. This side here, or this side, they're gonna be the same. Because the soil pressure here coming from this load is gonna be the same. And this length, most likely is gonna be the same as this length of the footing. It looks like a cantilever system. In a cantilever system, I'm gonna say, okay, here's a cantilever. Let's say this side, it's gonna be the fixed side of the cantilever. Where is the maximum moment? Is the maximum moment on the left or on the right?
On the right.
On the right. And the moment here equals to 0. End of cantilever, there's nothing there, right? So right here, moment is going to be equal to 0, and max moment is going to be here right at the face of the column. Someone's going to say, why don't I take the critical section for a moment to be inside the column? Again, say, if you take it here, here is one case, you take it here. Maximum moment is resisted by this depth of the footing. But if you take it here, it's true that you may have higher moment, let's give you resisted by the entire depth of the footing and the column. The entire thing here resisting this moment. So does it make sense when you consider the middle of the column, you just take it here at the face of the column. So I'm gonna say this critical section, right? I'm gonna put it this way. Moment critical section. Is gonna be at face of column. Where's the face of column? This is gonna be the face of column. This also is gonna be the face of column, right? In plan view, where is the section? Where is the face of column? In plan. Let's say in plan view, like in here, I'm gonna say this is gonna be the face of column. It's gonna be for this side. And for this side, this is gonna be the face of column. And for this side, this is gonna be the face of column. And then this side is gonna be the face of column. For this side here. Here's an actual plan, right? This is from an actual project. And you see here, footing is scheduled. We put the footing mark or the model. For example, this F8, usually we say it's gonna be 8 feet by 8 feet. Here's the thickness, here's the reinforcing bars, top and bottom. So sometimes we have top rebars, sometimes we have no top rebars, but for sure we have here bottom rebars. Look at the amount of rebars on the top compared to the bottom. Big difference, right? For number 5 versus 9, number 7. And when you look at this, it looks like all the top bars is gonna be the same, right? We just do it there for construction, for just fabrication, construction when you build the footing. But this is always gonna be doing work because they're exposed to tension. This one here, we ignore it. It's gonna be a few rebars. We just put it there so that we can tie in the column rebars. Here's the plan, and for each footing, it says here F10 means gonna be 10 feet by 10 feet. Here's an actual picture of the footing. You see here the top rebars, it's gonna be only few rebars on the top, and they're gonna be also small in size. And their job is just to hold the vertical rebars of the column in place. And you see here, when you look at the plan, the side looks straight. In reality, it's not really worth it to make it straight if you just make the hole a little bit larger. See here? So 10 feet actually goes to the face of this board, but we'll make it larger. And you see from this side, other board is coming by. But you need to understand that this footing was dig maybe 11 feet by 11 feet, or maybe 10.5 by 10.5, 10 feet and 6 inches. Here's the footing after we cast it, and you see here, they put the dirt back, and here's the column. Later on, they put some formwork for the column, just continue putting the entire building. Here's the building columns, casted already. So here without, and here's with the concrete casted. Another different of foundation. This one you have here, the footing, continuous footing for the wall during construction. Another big footing that maybe you can do it for one equipment. They call it flare. And here's the flare. Here's one piece of equipment. This is about 55 foot high. and the weight about 60,000 pounds in one footing. That's it. It's also one type of footings, right? And you have lots of anchor bolts here. How do we come up with the footing size? This will be the next question, right? The way that we do it, we have the vertical load coming from the column or the equipment or whatever. And then we have the allowable soil bearing pressure. This can be done here by geotechnical engineer. And then we say, if you take this axial load, divide by this bearing pressure, allowable bearing pressure, so you can get you the area required of the interface between the footing and the soil. Or maybe I can come here and say the soil pressure, Q, usually we say Q, equals P divided by the area. What area? I'm going to say the area and plan of the footing. This is going to be the contact area between the footing, concrete footing, and between the soil. P is going to be the vertical load. Q is going to be the soil pressure. This P is going to be the actual force, and this A is going to be the actual cross-section area. I can give you an example. I'm looking for Q when the axial load equals 600 kips, and the area is going to be 20 by 20. It's going to be 400 square feet. And this 600 is giving kips. So someone can come here and say, okay, in this case, the actual pressure below the footing. You open this up a little bit. The actual pressure here is going to be 600 divided by 400 is going to be 1.5 what? Kip per square feet. You can call it here KSF. Any questions? Excuse me. You better be sure that the allowable soil pressure is going to be higher than 1.5. So I'm going to say in this case, if Q allowable we call this Q sub allowable here. Is, let's say 2 KSF, 2 kip per square feet, then you are okay. If the actual soil pressure is lower than the allowable soil pressure, you're good. The problem is going to happen if this actual soil pressure is going to be above or higher than this 2 KSF. We're going to be in trouble. Now, this footing is going to be unsafe. It's going to be going through the soil. It's going to be penetrating the soil. So at the beginning, when we start our design, we have the vertical load. We have the allowable soil pressure, which is this one here. So the question is, how much area is needed in there? So I'm going to say, if you take this project back, start here from scratch, I'm going to say P equals 600 kips. Q allowable equals two KSF. You say the area needed, contact area, is going to be equal to 600 divided by 2 is going to be equal to 300 square feet. Are you guys following me? Yeah or no?
Yes.
So someone's going to say, select the footing size to be, you can say here 20 by 20. How much is the contact area provided? Let's say 20 by 20 is going to be 400 square feet. All right, so this 400 square feet is more than 300 needed, right? So my design is good. So it is either that you compare the actual pressure to the allowable pressure or the needed area, the 300, to the provided area.
So that I needed is like a minimum.
Yes, this is correct. This is what I need, required or needed. Exactly, this can be minimum. Good question. Now let's see this here in our equations. So, okay, that was just quick numerical example. Explain to what's going on. You can say, here's the equation. Area required, the needed one, is going to be equal to the P, like in here, the 600, and bearing capacity BC or Q allowable, right? In our case was equal to 2 KSF. Okay, yeah, it makes sense. Now this equation makes sense to me, right? And it's going to be the minimum area provided. One example says the column is 24 by 24 inch, dead load is 850, live load is 560. Square spread footing is going to be used here. The soil pressure, 7,000 PSF. In terms of kips, is going to be 7 KSF. And it says the most economical size for the proposed footing is going to be which one? You can see here they are talking about square footing. This answer is incorrect. This answer is incorrect. So I'm going to have either 15 by 15 or 18 by 18. So let me check this out. First, how much is the total load? I'm going to go back here to my slide. I'm going to say P service demand. How do you get here P service demand? P service demand is simply is going to be equal to 850 plus 560. No factor load. When I do the soil design, the pad size, length by width, is going to be just service. 850 plus 560. I'm going to try this here. 850 plus 560. Here is the vertical load. Your bearing capacity is 7 KSF. Divide this by 7 KSF. This is going to be the contact area needed. I just need 201.43 square feet. Which one would I pick? You can say, well, it's going to be square. Let's find out the square root of this value. It's going to be 14. If I use 15 by 15, I'm providing now 225, which is more than 201. So my choice is going to be 15 by 15 feet. Questions? Any questions? All right, I see a question here in the chat room. It says, is the footing depth determined by code, or is that something that's calculated? You can say, footing depth here, if I may take you back. It's gonna be like this depth, right? This depth here is needed because now we are gonna have a cross-section area of concrete. If I may cut a section this way and look the other side, you can have here a section like this. Here's gonna be the footing width in the other direction. This gives the footing depth from here to there, which is the same as this one. And say, well, let me just bring it down this way, right? And I have here some reinforcing bars, which is about here. So reinforcing bars is gonna be like this little box. Some reinforcing, it's gonna be right here. Now this depth is needed to resist the applied moment. So this is gonna be H in my analysis. This is gonna be D from the tension rebar to the total compression. So actually this depth is gonna be determined based on the strength of the footing that you'd like to accomplish. So I need to find out how much moment that goes to it. Here we're teaching, or we're covering concrete design. So the reason that I'd like to bring the foundations is that you understand the application of concrete design when it comes to foundation. At the end is going to be a concrete section with some bottom reinforcing, and I need to find out how much capacity I have in this section. It can happen in the beam, can happen in the wall design, can happen in the column design, can happen in the footing design. It happens in any structural member made out of concrete. This is the reason we're trying to understand how can I size the footing. When you size the footing, it means length and width, like in here in plan view, this length and width. You size it based on the bearing capacity of the soil itself. The bad thing that may happen if the amount of load coming to the footing is going to be above the allowed bearing pressure. This footing here is going to start to settle, which means it's going to start to penetrate the soil. This is going to be the type of failure or mode of failure, if you like, with the soil. Provided that the footing itself is strong, thick enough, has enough reinforcing, so nothing wrong is going to happen with the concrete member itself. For the sake of this course, I have two issues: sizing the footing like length and width. The second item is going to be design of the footing as concrete member, and then we need to see how can we design it. Good question, Chris. Any more questions, Chris? We are good. Yes. Answer to Nancy, yes. We choose smaller footing as much as we can. Of course, you'd like to go economical. Why would you go to by 18 feet by 18 feet if 15 is going to do the job? Just imagine that this guy here, you're building, right? Would you spend the money and put all of this material without the need to it? You say, no, we'd like to save as much as we can. So I'm not going to go here to 18 by 18 just to say it was 15 by 15.
Why did you cross out B and D from the get-go?
Because it's non-square. It says
Got
here,
it.
yeah, square footing, because the column also is square. If the column is square, you'd like to go with a square footing. Look at this. At the plan view, if the column is square, you'd like to set this cantilever length. Where's the cantilever? I'm going to say this can be my cantilever length, right? You want to set this length to be close to this length. Close to this length. To optimize the design when it comes to reinforcing. Close to this length, as much as you can. So if the column here is 2 feet by 6 feet, looks like a wall, right? The footing is going to be also rectangular in shape. So if the column is a square, footing is going to be square. If the column is rectangular, you'd like to do rectangular footing.
Thank you.
Professor?
Yes.
So if the column is circular shape, the footing is going to be in circular shape, right?
No, I do square. I'll tell you the reason. Just the cost of construction. Just think about putting a form work on 4 sides and make it flat or straight. It's going to be much cheaper than doing it round. So the column is round because most likely the architect would like to see it, right? It's like a artificial feature. But how about the footing? Footing is going to be just buried. Let's look here. You see, the footing is going to be below the soil. So here I may have a round column, but down below, no one's going to see it. So why should I go with round? Because the round footing is going to be more expensive. Does it make sense? Huh?
Yes, thank you.
Yeah, yeah. All right. Some footings are designed to support axial load and moment. So, okay, axial load and moment, I understand. I understand axial load and moment on a column, concrete column, but how about in a footing? I'm sure that you guys have studied this equation in mechanics of materials. When you have axial load and then you have moment at the same time. When you have an axial load, you take P divided by A. It's giving you the stress below the footing. Due to what? Due to P, the vertical load. When you have moment only applied on the section, the stress due to the moment is going to be equal to M divided by S. S is going to be the section moment. When you have combined loading, like P and M, you can do it with this equation. And in this case, you're going to have plus or minus. This one here is going to be compression, right? And let's assume for a second that compression is going to be positive value. So P over A is going to be positive, but this M over S at one side is going to be positive, at one side is going to be negative. The reason that we're going to have here plus or minus. Let me show you this. Here's your datum. Zero stress level. This here, I assume this to be positive value, compression, right? So you have vertical load, acting on the footing, you have pure compression on the soil. And here you have the moment. So this side is compression, right? And this side is going to be tension. If you want to figure out the stress at this point, I may call this here. Give me a second. Here's 2 points, 2 sides. You can say I have here 2 points. It's going to be point 1 or A, if you like to call it A, or just 1, it's okay. It's going to be point 2. Okay. How can I find out the stress at point 1 and 2? Maybe look in here. Here's point 1 and point 2. Same point, because actually this gave me 1 footing. I don't have here 2 footings, maybe just 1 footing. What happened? I'd like to figure out the stress at point 1 and the stress at point 2 under axial load P and moment separately, and then add them to each other. So I'm going to say the stress below point 1 is going to be equal here to P over A, which is F sub P. Let me go back. Here's F sub P, right? P over A. Due to the moment, it's going to be M over S. So at point 1 and point 2, because of this axial compression, I'm going to have the same stress level, F sub P, P over A. When I have moment, I'm going to have M over S as a stress level. But at item number 1 or point number 1, I'm going to have here tension, and number 2 is going to be compression. So at point number 2, the stress is going to be additive from FP to FM. You just add the 2 values. Let's say here that you have here 5 and here you have 3, total of 8. But on this side, it's going to be subtractive because the stress here is going to be opposite to the stress here. This is the reason that in this equation, I have here plus or minus. At the side where it's going to be additive, use the plus. Where it's going to be subtractive, use the negative sign. Is this clear, or any questions on that? Yes? No questions? Okay, good. The tricky part, when I have the stress value here in one side, is going to be really different from the stress on the other side. Let me show you here the case. At one case, when the amount of tension is going to be smaller than the compression, you're going to end up with this distribution. Another case, when the amount of tension is larger in value than the compression, you may end up with this solution or distribution. Let's try this here numerically. So I'm going to say here P over A, I'm just going to assume here P over A is equal to 5 KSF, kip per square foot. All right? Are you guys following? Yes? All right. M over S is equal to 3 KSF. So stress here is going to be 3 compression, 3 tension. It's going to be here 5 compression. At point number 1, I'm going to say final stress at point number 1. And I put it right here, which is the stress here. Adding the stress coming from this side. Stress at point number 1, I'm going to put it like this. Q equals I'm gonna say 5 plus 8, 8 KSF. 5 plus 3, 8 KSF. You say, how about the stress at point number 2? How much are we talking about? You say problem number 2, you're gonna have 8 compression, right? Is it 8? No, it's 5 compression, negative 3. That's why it says here plus or minus. It's gonna be equal to 2. Is this 2 compression or tension? Give me the question to you guys. Should I ask someone? Gabriel? Are you there?
He typed it on chat.
So this 2 is gonna be compression or tension? See if Gabriel says compression. This is correct, Gabriel. It's gonna be compression because I assume compression to be positive. So this is good. I'm done with this. I'm gonna say, okay, let me change here the case. I need to change the values a little bit. I'm gonna say, let's assume here for a second. Just put this here for now. I'm gonna assume for the second problem or second case, I'm gonna say if P over A is equal to 4 KSF. Just assuming, right? And M over S is equal to 5 KSF. Then we figure out here the stress at 1 and then figure out the stress at 2. The stress at 1 here is going to be 4 plus 5. It's going to be 9 KSF. But at point 2, it's going to be subtractive. So here, how about point 2, right? What's going to happen there? You're going to say it is going to be 4 minus 5. It's going to be minus 1. Is this negative 1? Is it tension or compression? Elias?
Would it be tension?
It's going to be tension. Now the question is, can you have tension on the soil? Can the soil take tension?
Isn't it ripped out?
It cannot. Can the soil take tension? Just imagine that you have here your hand, right? Or your foot. Let's say that, try to think about as a foot, right? As a footing. Can you put your foot here, start to pull it up, and then you see resistance from the soil or the floor? Is there anything the floor to bring your foot down? It does not. It's gonna be lifting up. And all of a sudden you see here a gap between your foot and between the floor, right? Same thing with your hand. If I put my hand here on a table, just start to lift it up. Is anything here resisting the uplift? There's nothing. Correct? You guys agree? Or you don't feel this?
Agree.
Yeah, I mean, there's no resistance. So this is gonna be an issue because it means if I have lots of moment in the footing, I can just apply this equation. This equation is good as long as P over A is gonna be greater than M over S. So what can I do in a case like this? The only way that you do it, right, if you develop a new set of equations. I have here two cases. If FP, which means compression, is gonna be greater than the stress coming from the moment numerically, I'm gonna have this case A. Case B is gonna happen when the amount of moment is gonna be just high. I'm gonna show you here some pictures. Here is when you have the axial compression is much higher in value than the moment. But when the moment is getting great, what's going to happen is going to lift up. You're not going to have here any contact pressure. And I have here a couple of equations for you to figure out this F1 and this distance 3 times x. If you like to study this analysis and foundation, this is fine. You can take your time. It's going to be about foundation design. This is going to be like geotechnical stuff, soil engineering. But for me, I'm going to say I'm just going to be following the equations. And the stress distribution is going to be different. Okay, good. I have some examples here. Here's one footing. Here's the size of the footing was given to me, 10 feet and 12 feet. 600 kips is going to be the service load, vertical load. Moment 720, also at the service level. Let's say first, the maximum soil pressure under the footing. So, okay. Remember this, 600, 720, footing is 10 by 12. 600, 720, length is going to be 10 by 12. Contact area of the footing with the soil, 120 square feet, 12 times 10. Section modulus, because the moment is acting this way, it's going to be BL squared divided by 6, very similar to the one that we did with the cracking moment. It's going to be 240 cubic feet. It's going to be for S. Now we have P over A, M over S. Same numbers that I was working with, right? You remember these numbers? Yeah, 5 and 3. So, okay, same numbers. Due to vertical load, I have 5 KSF. Due to moment, I have 3 KSF. It means one side, here's F1. It's going to be how much? 5 minus 3. Because compression is going to be coming this way, tension is going to be in this side. And the other side is going to be 8. 5 plus 3. Okay, good. Now I understand this. I have a numerical example for it. Second example, it says moment stayed the same. Look at this moment. 720 is the same moment. Vertical load dropped from 600 to 240. So now I'm giving you the other side, right? The other example, the other case, case B, when you have lots of moment compared to the axial load. As if the moment wants to flip it and the axial load wants to stabilize it, just to bring it down. When I did the analysis, P over A now becomes 2, but if M over S, the same coming from the moment, is going to be now 3. Now, when you look at this, you say now, moment stress is going to be higher than the axial load stress. So I'm going to have here an uplift case. Footing is going to start to lift up. I can't really use this equation. I need to do the other sets of equations, and F1 would become 5.33. This equation is based on what? It's based on L, the length, total length of the footing, M over P, which is eccentricity, right? Yes, here, M over P, 720 divided by 240, moment divided by axial would give you this amount of eccentricity, 3 feet, and give you here the dimension 3x, and the stress, and now I'm done with the stress analysis. I'm going to be more interested in the concrete design, not in the soil engineering design. But it is good to understand, because whoever is going to be structural engineer or civil engineer working in the structure business, you need to understand this design very well. Now, after this, we're going to be working on combined footing, and this combined footing means a footing, one footing supporting 2 columns. It happens a lot. When the 2 columns are coming close to each other, they're going to be kind of overlapping. So let's say for the first column, I need the footing of this size. Let's say like this. For the second footing, I need, for the second column, second footing, I need something like this. Now the overlap. So what I say, you know what? Let's just make him as one footing. It's going to be cheaper and easier in construction. I said, okay, and maybe I can do here one big footing. So I need to combine it. I have the column loads. This is going to be very important, right? Dead load and life load for each one of the columns. This is called here C2 and C4. And they have the footing size that I need to solve for. It's going to be very important that I know the spacing between the two columns. Otherwise, why don't I just do them like this? If the distance is too big, right? One column, one column. So when the distance between the two columns is kind of getting closer, like in my case here, maybe I can develop a one, right? Just one combined footing. Does it make sense? Any questions? All right, we'll continue next time. Would you please go ahead and sign out, type your name in there in the chat room. And I'll see you next time.